All right, so again, welcome to the first webinar in the complex series of the year. This is Parallel Computing Concepts, and I'm giving this on behalf of the SCSC complex team. So for those of you who are new to complex, just want to mention that this is I need to update this. We've been around for a little more than 2 years now. It's a newish SCSC program where the training covers the non-programming skills needed to effectively use supercomputers. And topics include parallel computing concepts, Linux tools, bash scripting, security, batch computing, how to get help, data management, and interactive computing. And we are supported by the National Science Foundation. So let me kick things off here with a little bit of an introduction. So I'm going to say the reason excuse me, that most of you are here is that your workloads have grown to the point where you can no longer run them on your local resources. I do a lot of small scale computing myself, and I find it very convenient, to just open my laptop and start running. But we also have much larger problems that do require supercomputers. And specifically, you may need to use what we call parallel computing. So this session is intended for anybody who currently runs, plans to run on, or is thinking about running applications on parallel computers. If you're going to be writing a proposal for computer time, say in your campus cluster, nationally allocated systems, or other resources. So generally, if you need a small amount of time, it's pretty much there just for the asking. But if you need larger amounts of time, as we get into the hundreds of thousands or even millions of CPU hours, or say tens of thousands of GPU hours, it's often a very competitive process. And from my years of experience with the exceed and access allocations process, I would see over and over again that the number one reason that requests for time are not supported is due to the justification for how the number of CPU or GPU hours was arrived at, or a poor presentation of scaling data. If you're purchasing time and compute resources and you want to maximize the return on your investment, let's say you're going to the cloud, or if you're considering purchasing hardware for your lab. And finally, if you're just curious about parallel computing, you're more than welcome here today. So the motivation for this talk and kind of the complex series in general is that much of the training in parallel computing, it's targeted at people who write their own parallel applications, and it often focuses on programmer topics, MPI and OpenMP, CUDA, profiling, performance tuning, all very, very important topics. But if you're not a developer, if you're primarily using third-party software, applications that somebody else has developed, you probably don't get a good introduction to parallel computing. So even if you don't write code, though, it's still important that you understand some of the basic principles of parallel computing so that you can make the most effective use of this very valuable advanced cyber infrastructure. So just to dispel a few myths, and I hope for all of you here that these are myths, but they're still kind of kicking around. Every once in a while, I might be at a party or get together. We talk about what we do. I mention I do supercomputing, and folks who don't work in this area, often have a certain myth. They say, "Oh, supercomputing, that's for the astrophysicists and engineers and climate modelers and other traditionally math-intensive fields." This might have been partially true decades ago, but today nearly every field of research makes use of parallel computing. And we've been seeing a big uptake for the social sciences, life sciences, arts and humanities, and of course, in addition to the usual suspects in physics, chemistry, engineering. Now, the biggest myth that I encounter is that throwing more hardware at a problem will automatically reduce the time to solution. And the reality, though, is that parallel computing is only going to help you if you already have an application that has been written to take advantage of the parallel hardware. And even if you do have a parallel code, there's going to be an inherent limit on the scalability, and much of this talk is going to address that. Now, there's one caveat, and that's if you have a high throughput computing workload, where you can use parallel computing to run many single core or single GPU instances of an application to achieve near perfect scaling. And later this year, we will be having a talk on high throughput computing. And then finally, and I talked about this a little bit already, the last myth I'm going to address is that you need to be a programmer or a software developer to make use of parallel computing. And the reality today, though, is that most of the users of our big supercomputers, they are not programmers. Instead, they're using mature third-party software that had been developed elsewhere and made available to the community. So in a nutshell, there's a very, very good chance that you're going to be using someone else's code. And over the years, I've worked with many, really brilliant computational chemists, material scientists, bioinformaticians, folks from nearly every field who were big users of supercomputing, but they weren't programmers. And I think this is great because it gives you the opportunity to really focus on your science and not have to split your time between being a developer and a scientist. Now, I know there are a few folks out there who kind of serve both roles, but for the most part, we're beginning to see more of a division of labor. So parallel computers, a lot of you are probably familiar with this already. The modern clusters in parallel computers, they consist of multiple compute nodes connected together by a fast network. Each of those CPU nodes is going to contain one or more, typically two multi-core processors. So you have a lot of parallelism right there within a single node. The GPU nodes are typically going to contain 4 GPUs, although some of the newer hardware is going to have 8 GPUs in the node. And to effectively use this hardware, you need applications that have been parallelized, specifically written to run on multiple cores or multiple GPUs within a node or across multiple nodes. Okay, so getting a little bit into the technical details now. So terms that you might have heard thrown around over the years include threads and processes. And there's often a little confusion over what is a thread, what is the process, and what is the difference between them. So you could think of a process as an instance of a program with access to its own memory, state, and file descriptors. That simply means that a process can open and close files. Now, a thread is something a little more lightweight. You could think of this as something that executes inside of a process. So every process by default is going to have at least one thread. And then this is a really, really important point. Threads within a process can access shared memory. So whereas a process, you could think of each process as kind of standing on its own, having its own memory, state, and so on, threads can access a pool of shared memory. And that's going to be really, really important when we develop and execute these parallel codes. Now, I did a little bit of searching online to find some articles that describe the differences between threads and processes. Now, a lot of these tend to be geared toward computer scientists, but I found 2 resources that I think do a pretty good job of addressing the topic. I'm going to suggest that you go to the second link first if you want to explore threads and processes. There's a really good talk on educba.com, and it's a little more informal. And then if you feel like you want to go a little deeper, maybe go to this Stack Overflow thread. Okay, talking a little bit more about threads and processes, they each have their advantages and disadvantages. So a process is going to incur more overhead, again, thinking of a process as an instance of a program, but they're also more flexible. We can run multiple processes within a compute node, or we can write parallel applications involving multiple processes that span multiple compute nodes. And this is what we call distributed memory parallel computing. Now, threads, they have their own advantages and disadvantages. A thread is going to incur less overhead. Threaded codes can use less memory since threads within a process have access to the same data structures. The downside, though, is that threads are less flexible. Multiple threads associated with a process can only be run within a compute node. So what we call shared memory parallel programming. Okay, so why do you care about processes and threads? The type of parallelization is going to determine how and where you're going to run your code. So distributed memory applications, multiple processes or instances of a program, these can be run on one or more nodes. Now, shared memory applications, you're going to have to run them on a single node, where all of those threads have access to that same pool of memory. Now, a lot of modern applications will mix these two types of parallelism, and we call these hybrid applications. These can be run on one or more nodes, but we need to often consider the balance between threads and processes, and we'll talk about that soon. And in many cases, you'll need to consider how the processes and threads are mapped and bound to cores. So it can impact the performance of our code. Say if the threads are migrating from one core to another, might involve some extra data movement. So if you're aware of threads and processes, it's going to help you to understand how your code is utilizing the hardware and help you identify common performance and scaling problems. Okay, so we're going to talk a little bit about two topics that we're not going to go into much detail on. These are really programming topics, but I want you to be aware of what these are. So you're going to hear the term message passing interface. So MPI, this is pretty much the standard for parallelizing C, C++, and Fortran code to run on distributed memory or multiple compute node systems. So we like to say that it's really a de facto standard. It's not officially adopted by by the major standards bodies, but it's available pretty much everywhere. So when you see the really large parallel applications, the ones that are running across substantial fractions of a supercomputer, they are almost always developed using MPI. Now, there are a few exceptions. I'll mention that in the last bullet, but MPI is still dominant. Now, there are multiple open source implementations of MPI. So you might hear terms like OpenMPI, MVAPITch, and MPITch, along with vendor-supported versions. So again, these are just different implementations of the MPI standard. Now, MPI applications, they can be run entirely within a shared memory node, and you might find yourself doing that more and more as the number of cores that we pack into a node grows. Currently, Expanse has two 64-core processors for a total of 128 cores per node. And we could easily envision future machines that will have 256, 512, or even more cores per node. So there's a lot of parallel computing we can do within that node. MPI is portable and it can be used anywhere. So on any cluster, all you need to do is install MPI, or more likely your sysadmin or the folks who manage these computers at the supercomputer centers. But you're going to find MPI pretty much everywhere. Now, MPI is often synonymous with distributed memory parallelization, but there are other options that are gaining adoption. The one that I think is most widely used is something called Charm++, and that's used to parallelize the NAMD molecular dynamics code, among with others, but I think that's the major application to date for Charm++. All right, although we're discussing MPI, the same principles that we discussed here are going to apply when parallelizing deep learning applications. So you might come across things like Horovod. This is a distributed deep learning training framework for TensorFlow, Keras, PyTorch, and MXNet. And Nickel, this is the NVIDIA Collective Communication Library, which is used for multi-GPU and multi-node communications. This is optimized for the NVIDIA GPUs and networks. But the issues that we run into with MPI are the same ones that we're going to see when using, say, Horovod and Nickel. All right, so I'm going to show you an example of a code that's been parallelized with using MPI. Now, this is a Um, but I'm going to say maybe not a typical MPI example, because we're going to see that the amount of code that we had to add to parallelize this very, very simple C program, hello world, really expands the code base quite a bit. For real applications, I'm going to say the MPI portion of the code is going to be much smaller, but it could still be substantial. Now, again, I know that that this isn't a talk for programmers or developers, but I just want you to be aware of MPI. So if we decide to parallelize this hello world, you can see that we're going to start off by adding a header. We have some code where we initialize the MPI environment. And this is really important because when we initialize the MPI environment, what we're doing is we're creating multiple processes that are going to be communicating with each other. Many MPI codes are really running multiple instances of that program, and then they're communicating with each other using various MPI library calls. And what's going to distinguish each instance of that program typically is just going to be the rank. So let's say we're running 8 processes labeled 0 through 7. Initially, the only thing that's going to distinguish those instances of the program are going to be that rank. That's going to determine who they're going to communicate with, what portion of the data they're going to read, what portion of the data they're going to write out. So you can see here that we do the initialization, we get the number of processes, we get the rank of each process. Optionally, we can get the name of the process, the name of each processor that the process is running on. And then finally, we get down here and we print hello world, except here we've modified it to have each process write out its rank. So again, you don't need to know MPI, you just need to be aware that it exists. And if you are building your own application, let's say you download the source code, when you build it, you're just going to need to make sure that you use the appropriate wrappers. Now, OpenMP is a different approach to parallel programming, and this is for shared memory parallel programming in C, C++, and Fortran. The approach is a little bit different. OpenMP provides a collection of compiler directives, library routines, and environment variables. So remember, for OpenMP, we're managing threads, multiple threads that are executing within a process. Now, OpenMP is supported by all major compilers, including IBM, Intel, GCC, PGI, and AMD's optimizing compiler collection. Like MPI, OpenMP is portable and it can be used anywhere. And although OpenMP is often synonymous with shared memory parallelization, there are other options out there, such as Silk, POSIX threads, and specialized libraries for Python, R, and other programming languages. And just to show an example of how code is parallelized using OpenMP, again, if you're not a programmer or an application developer, you do not need to know OpenMP, but you do need to be aware that it exists. And if you are building your executable, you'll need to use the appropriate compiler flags. And these can vary from compiler to compiler. And we're going to have a talk later this year that talks about building parallel applications. So this is what a parallelization of this simple piece of code looks like using OpenMP. We have a header, we have some definitions at the top, and then the primary thing that you're going to be using in a code that you're parallelizing with OpenMP is going to be pragmas that describe, and you can see this down here at the bottom, that describe how iterations of a loop are spread out across the multiple threads. So there's more you could do with OpenMP, but this is the most common use. Right, so when you're building an application, if you need to start with code and you're compiling it, you need to keep in mind that MPI and OpenMP work a little bit differently. So processes are managed using MPI. So MPI is going to handle the communications between processes, typically multiple instances of a program, and MPI is implemented in libraries like mpitch and mvapitch and OpenMPI and vendor implementations. Now, threads are going to be managed using OpenMP, and OpenMP is implemented by the compilers, GCC, Intel, PGI, and AOCC, among others. So to date, I haven't seen any major compilers that do not support OpenMP. So I saw that there were a few comments in the chat. So Cindy, are there any questions for me to answer?
Nicole has kindly responded to one, but there's one that's open. The question is the classic map/reduce approach using one of the types of parallelization you are discussing?
Yes, you could. So MapReduce is something that we usually think of with Hadoop, but you can do that same thing in MPI. You could designate one process to be I guess what we call the leader, which would oversee the distribution of work to all of the other processes and kind of managing that process. So I'm going to say Hadoop is more popular, especially outside of the science and engineering parallel computing world. It's much, I'm going to say, more straightforward to use. And when you work with MPI, you kind of feel like you're somewhere at the level between C programming and assembly. It's very, very low level. But yeah, you could um, use MPI to manage that kind of a workload.
Thank you, Bob. Two more questions.
Yes.
Can you comment on MATLAB parallel processing on a node across multiple nodes?
Ooh, I'm not terribly familiar with how MATLAB does parallel processing. But I can say though, if you have MATLAB code that is running across multiple nodes, it's going to be doing something under the hood to manage the communication between those processes. And again, I haven't worked with MATLAB in a long time, but if you work with, say their toolkits or their parallel libraries, they're going to have that implementation. They're going to have that implemented under the hood. But I'm just going to stop there and not venture too much into a topic I don't know much about. And
Thanks,
Cindy,
Bob.
there's one more question.
Correct. Is there a limit to the amount of threads that can be executed within a process? I imagine that the only requirement is that the amount of memory shared among threads is sufficient.
Okay, so let me address that last part first. So as you spawn more threads, you really don't need more memory. Um, Yeah, threads are very, very lightweight, so threads are going to have access to the shared data structures within that process. Now, the answer to the limit on the number of threads, I'm going to say it's kind of a yes and no. So normally, you would want to have one thread per core. But there's no reason that you're strictly limited to that. You could have two threads per core or four threads per core or so on. But what's going to happen though is that those threads are going to be competing for resources. So if you use a tool like top to see how much of the CPU each of those threads is consuming, if you were running one thread per core, you would ideally see that the CPU utilization is topped out at 100%. But if you had two threads per core, you'll typically see that each of those threads is using half of the CPU. So generally for HPC, science and engineering applications, you are going to practically run one thread per core. But if you run more, nothing's going to prevent you from doing that.
Bob, two more came in. Do you want to take that now?
Yeah, I'll take that now.
Okay, so next one is going to be when running an MPI program on a single computer, will different processes still use the network stack, same as the cross-node case, for message exchange, or the message exchange will go bypass the network stack?
Yes, that's a great question. Now that's gonna depend on the MPI implementation. The MPI standard says nothing about that. But in all good implementations, like all of the ones that I mentioned, they are going to be written, the MPI library written in such a way that it will do the communications in the most efficient way. So you're not going to be going through the whole network stack. If you're communicating between MPI processes that are on a single node. I remember years ago there was a library, it was called LIMIC, LIMIC, which addressed that, which ensured that you were doing optimal intra intranode communications. But I think nowadays all of the MPI implementations address that, and they'll make sure that you're not going out and using the entire stack. I don't know all of the details, but they're going to circumvent um, going to the whole stack. Yeah, great question. And Cindy, there was one more.
Correct. Modern compilers include the option to perform automatic parallel implementations. Is this safe? Any comments on this?
Okay, so I'm going to say it's not. I'm not aware of it being unsafe. But keep in mind though that the parallelization that the compilers can do is limited. So it might be able to do parallelization within a node, this shared memory parallelization, but I'm not aware of any compilers that can do, MPI style parallelization, where it will figure out how to do the communications between processes and different nodes and manage that. So um, yeah, so in a nutshell, I'm going to say it's not unsafe, but it may not do everything that you think it's going to do, and it will limit you um, to running on or to doing the parallelization within a single node. And I know this isn't an OpenMP talk, but there are some things that I could see that it wouldn't be able to do. For example, if we are parallelizing a loop, it might just do the simplest parallelization and say we're going to take the iterations and we'll just divide them evenly across all of the threads. Whereas if you had an imbalance in the amount of work being done by each iteration, for example, I had worked on a computational finance program years ago where there was about 5 orders of magnitude difference um, between the fastest running and the longest running iteration. It wouldn't be able to handle that. So I'm going to say safe, but the capabilities are going to be limited. And Cindy, any more questions?
That's all. Thank you, Bob.
Okay, great. Yeah, thank you, everyone. Those were fantastic questions. Okay, so now we're going to get into hybrid applications. So we talked about you using MPI to parallelize processes and OpenMP to parallelize cross threads. But you're going to find that many modern parallel applications are built using a hybrid approach that takes advantage of both distributed and shared memory. So years ago, many years ago, when the number of cores on a processor was very modest, say 2 or 4 or 8, applications would often be parallelized using just MPI. We'd find that you didn't get much speed up if you tried to do this combination of processes and threads. But now these nodes are really fat. We now have routinely 128 cores on a node, and we're going to be looking at 256 and 512 and more in the future. So we're seeing more and more of a combination of MPI and OpenMP. So these hybrid codes have advantages over purely shared and distributed memory apps. So of course, the shared memory apps, they can only run within a node. It cannot be used to run across multiple nodes. Now, the distributed memory applications may have higher memory requirements and more overhead when running within a node. So you often find that if you can run, say, a small number of processes within a node, and then multiple threads within each process, that we can get better performance and a lower memory footprint. So we're going to look at a very simplified parallel computer. So this is just two nodes, each with 16 cores, and they are joined by a network. So these blue squares are going to be cores, the big gray box is going to be a node, and that black line is the interconnect. So if we're running a straight message passing application, we would typically have one process per core. And this example shows running 32 processes across two 16-core nodes. So we have one process associated with each of those cores. Now, if we have a threaded application, again, we're going to be restricted to running within a single node. So here we might run a single process and then use all those cores. Or say if you're on a machine like Expanse where we allow shared use of that node, you might be running a single process across the cores that were allocated for your job. Now I have a star here where I say technically any programming model can be mapped to any hardware, but in practice, threaded apps are run within a single node for best performance. We had a supercomputer 2 computers ago where we had this innovative feature where we're using software that would aggregate multiple nodes and make it look like a large shared memory machine. But we found that the performance was actually terrible because every time you were accessing the memory from another node, you were initiating the communications. So again, think threaded applications stick to a node. What we're seeing more and more of today, though, is a combination of threads and processes within a node. So here we show 2 processes per node and 8 threads per process. The old scenario was to run 1 process per node and threads within a node, but this is becoming a little less common as we're getting more and more cores within a node. So for these hybrid apps, we can run anywhere from 1 process per node to 1 process per core. And this is a little bit of an art. You may, for your applications, you may need to do some benchmarking to figure out what this right balance is between threads and processes. So let me talk a little bit about scalability. So one of the things that I mentioned early in the talk is that you can't just keep throwing more hardware at your problem. Your code is going to have a limit, a real cap on the speed up that you can get as a function of the number of processors. So if you know just one formula, one law from parallel computing, it should be Amdahl's law. So we're going to say that P is the fraction of the code that can be parallelized, and S is everything that's left over, the fraction of the code that must be run sequentially. And when we say fraction of the code, and I should probably reword this, I don't mean the number of lines of code. I guess a better way to put this would be P is the fraction of the work that could be parallelized. And N is going to be the number of processes or processors. So we're going to see that the speed up as a function of the number of processes is going to be 1 over 1 minus P, so the serial component, plus P over N. So we're taking the parallel work and we're going to divide that across multiple processors. So as we increase N, the time that we spend there is going to continue to decrease, but we're always going to have that little bit of serial work left over. So if we run on an infinite number of processes, not something that you're ever going to do, and we're not going to let you ever run on the entire supercomputer just so you can get out to this limit, you're going to find that the theoretical max speedup is going to depend only on the proportion of the serial content. And we're going to show in the next slide, it doesn't take much serial content to quickly impact the speedup. So here's a figure I put together showing the speedup as a function of number of cores for code with 50, 75, 90, and 95% parallel content. And we can see that the maximum speedup that we get ranges from 2 for 50% up to 20 for 95%. And let me add one more curve on there. And this is for code with 99% parallel content. So you can see there that the maximum speed up we could get in that case with just 1% serial content is going to be a speed up of 100. And even then, I'm going to say if you have a code with 99% parallelizable content, you don't even want to use an entire, say, expanse compute node, which has 128 cores. So you would be using 128 cores and only getting a speed up of about a factor of 60. So we would want you running somewhere a little bit further to the left on that curve. Now, if that's not bad enough, Amdahl's law only sets a theoretical upper limit on speedup, but there are other factors that are going to affect scalability. There's the problem size, communications, uneven load balancing. So in real-life applications that involve communications, say synchronization, where all the threads of the processes must complete their work before proceeding, irregular problems, non-Cartesian grids, the speedup can be much less than predicted by Amdahl's law. So let's start with problem size limitations. And I need to eventually get a new figure here. When I put together these slides, the only public domain image I could find with a transparent background of a character with paintbrush was Hello Kitty. So let's say we have one painter working on a fence, might take 48 minutes to paint the fence. And it would seem logical that if we double the number of people working on this, we have 2 painters, that it should take 24 minutes. Maybe 4 painters could do this in 12 minutes. 8 might be able to do this in 6 minutes. But we get to the point where there's, say, 32 workers. There's just not enough fence to go around for those 32 workers to give you much speed up. Eventually, you'll get to the point where your code may actually run slower because you have all of this overhead involved with all of those processes and just not enough work to do. Another limitation is going to be something that we call uneven load balancing. So parallelizing a code requires dividing the computational work into chunks that can be executed independently. Now, if the work can't be distributed evenly, then processes are going to be sitting idle, waiting for the longest chunk to finish. Now, this isn't going to apply to all applications. There are many, many applications where load balancing can be achieved very easily. But getting back to that code that I mentioned earlier in computational finance, where each chunk could range from requiring less than a second to complete to maybe close to an hour, we really ran into some very serious load balancing issues. So let's take a case where we have these chunks of work that we're going to assign to processors 0, 1, 2, and 3. And let's say that after we assign the work, we can't proceed until everybody finishes their first task. So you're going to see that if we have an uneven load balancing, we're going to have a lot of times when the processes are idle, waiting for the longest running process to finish. Okay, and finally, a really, really common issue is communications overhead. So if you're working in an area, say, where you're solving systems of partial differential equations, this is going to be computational fluid dynamics, magnetohydrodynamics, climate, weather, oceanography. You're often going to take your computational domain, you're going to convert it into a grid of cells, and if we're trying to parallelize this, we are going to take a portion of that grid and we're going to assign it to different processes. So this is an unrealistically small problem. We're never going to use a supercomputer or parallel computing for a 16 by 16 grid, but just imagine that we're going to scale this up. So we're going to take this grid and we're going to divide it into 4 8 by 8 chunks that are distributed across processes. And let's assume that each of those cells is going to be updating using the values of the 4 neighboring cells. This is a very, very common stenciling operation that's used in finite difference calculations. Now, for the cells that are within the interior of each chunk, those calculations can be done entirely within the process. But for the cells at the boundaries, they're going to need data to be communicated from the neighboring processes. So to do this, we're going to have to add a halo of host cells, and data must be communicated between the processes. Again, this is something you don't need to worry about as the end user. The application developer would have done that. So now we need to, we're going to have some overhead due to this communications between the processes. And Cindy, do we have more questions? I see a few more in the chat.
Yes. One is, what is the setting consuming less memory? Can a dynamic memory management be configured with MPI?
I'm sorry, could you repeat the last part?
What is the setting consuming less memory? Can a dynamic memory management be configured with MPI?
Ooh. So I think the memory management that you're talking about is going to be something at a lower level. So typically each process will be will be assigned a certain amount of memory. So let's say where we have multiple MPI processes running on a single node, say it's 4 processes, each of those would have a quarter of the memory. So I don't believe that there's a way, if you're talking about memory management, to kind of shift that between processes. But within each process, there is going to be memory management, but again, that's at a much, much lower level. You might be thinking of, the way memory is allocated and freed, say explicitly in a C or C++ program, and sort of the garbage collecting that the operating system is doing. So if that didn't answer your question, just stay on at the end of the call and we can discuss that further. And Cindy, any more?
Yes. What is the best way to break up the grid and distribute when solving CFD in a cylindrical coordinate system?
Ooh, that's a very, very detailed question. Yeah, I could picture that. Again, that's going to be something that I'm going to say we're not going to get into here. That's going to be for the for the application developer. What I might do, I mean, just off the top of my head, I would well, it also depends on the dimensions of the system. If it were a very, very, if the cylinder were very long, relative to the relative to the diameter, I might do a one-dimensional decomposition where I just kind of slice that cylinder into chunks and then communicate between them. If you had a um, if you had a smaller aspect ratio, I'd probably do a 2D decomposition where I divide it into slices and then maybe divide radially around the cylinder. But yeah, again, that would be something for the developer to address as opposed to an end user.
So
And
follow on to that question, Bob. So slices in Z?
slices in Z, yes, yes. So I think of it as like slicing a salami. But again, that's going to depend a lot on the specifics of the calculation. So let me move on. We only got about 10 minutes left, a little bit more material to get through. So at this point, you're looking at the limits imposed by Amdahl's law, and then we have all of these other factors that affect scalability. You might be wondering, how does anybody ever get to use all the cores on a single modern compute node, let alone a full supercomputer? So first of all, the reality is that most parallel applications do not scale to thousands or even hundreds of cores. We find on machines like Expanse that most users have a much more modest parallelism. They might be running anywhere from 1 core to dozens of cores, and they they would just kind of cap it there. Also, there are ways that you can achieve higher scalability, growing the problem size, overlapping communication with computation, dynamic load balancing, and I don't get into this last bullet, but this is doing a computation where you have more computation relative to the communications. So getting back to the problem size limit, we don't keep throwing more hardware at the fixed size problem. Instead, we say we have more processors, we have more memory, we're going to solve a larger problem. So in this case, if we had our 32 painters, we wouldn't use them to paint a small section of fence. We would use them to paint a much larger section of fence. If we were doing something like climate, again, we wouldn't do a climate or weather simulation. We wouldn't do a very, very coarse grid on a large supercomputer. Instead, we would go finer and finer and finer. We would be solving a much larger problem. Now, communications overhead, and again, this is going to be something that the application developer will do, is we can overlap the communications and the computation. We can communicate data while we're working, say, on those interior cells, so that when we get to the cells around the edge of the domain, the data is already there. So it's a little bit more sophisticated implementation, but again, that's going to be on the burden of doing that is going to be on the application developer, not the end user. And we can use dynamic load balancing. So, imagine we have a set of tasks that could all be performed independently, but they take varying amounts of time. Instead of doing a static assignment, which could lead to a very large load imbalance, we could dynamically assign work to processors as they become idle. So let's say that we had these 8 tasks. We're going to call them, label them A through H, and we're running on 2 processors. So let's say we just assign the first 4 tasks to processor 0, the next 4 to processor 1. And we're going to go into this assuming that we really don't know how long each individual task will take. So if just by chance those 2 long-running tasks, A and B, were assigned to processor 0, we would have a very large load imbalance. But instead, if we handed these out as each processor became free or idle, we can see that we can make much, much better use of the hardware. And this was the approach that I had taken when I parallelized the computational finance application I mentioned earlier. So I'm going to get to one more topic, and this might be the most important takeaway for this entire talk. And that is running parallel applications. So we talked all about, hardware, threads, processes, Amdahl's law, other factors that affect scalability. So all of that theory and background is great. But how do we know how many CPUs or GPUs to use when running our parallel application? And I'm going to say the only way to definitively answer this question is to perform a scaling study where a representative problem is run on different numbers of processors. And by representative, I mean one with the same size, say grid dimensions, number of particles, number of images, and so on, and complexity, say it's computational chemistry, the level of theory, the type of analysis, the physics, as the research problem that you want to solve. Now, that doesn't mean, let's take the example of computational fluid dynamics, that we need to run the full number of time steps on 1 node, 2 nodes, 4 nodes, and so on. We just need to run, a limited number of time steps so that we can figure out what the scalability is going to be. So this is something that we see all the time in allocation requests. And I noticed, on the list participants that there were at least one reviewer who I recognized. And this is something that drives us nuts. Believe it or not, these scaling curves are for 2 completely different codes. One of them scales very well, the other scales terribly. But when you look at these plots, it's impossible to tell which is which because we're using linear axes. Now, if I plot that same data again on log axes, we get a lot more insight. So notice that I have log time versus log number of cores. So now if we have linear scaling, we're going to be getting straight lines. And I have a black line on here to indicate linear scaling. So you can see the figure on the left, we have an application that gets perfect scalability out to 128 cores. On the right, we see that we do pretty well out to maybe about 16, maybe even 32 cores. But after that, the speed up, the what we call the parallel efficiency, the speed up divided by the number of cores, kind of drops off. So where should you be on the scaling curve? I'm going to say that if your work is not particularly sensitive to the time to complete a single run, consider using a CPU or a GPU count at or very close to 100% efficiency, even if that means running many instances of your code, each on a single core. Now, go a little further out on the scaling curve if the job would take an unreasonably long time at lower core counts, or if a shorter time to solution helps you make progress in your research. If your code does not have checkpoint restart capabilities and the runtime would exceed queue limits, then you might have no choice but to run at higher core counts. And then, if time to solution is critical, it's okay to run at lower efficiency. This is going to be more common, say, if you're running on hardware that's dedicated to your project. So let's say you have your calculations are tied to, say, data collection. So you collect data every day, you need to process it overnight. There you might want to run at a lower parallel efficiency as long as it's still making gains. And if it's something really, really critical, and I don't think anybody here is doing this, but if you're working, say, for the National Weather Service and you're doing tornado or tsunami prediction, running as much hardware as you have, as long as you keep reducing time to solution. And I'm going to skip over the comment on large memory footprint, but be aware that sometimes you might need to run on more nodes just so that you get enough memory. So I'm going to wrap up here. I'm going to say we just scratched the surface. We didn't tell you how to do parallel computing. We just told you, I think, what are the important points and how to do a scalability study. A lot of additional resources out there. So I'm just going to wrap up and say parallel computing is for everyone who needs to accomplish more research, solve bigger problems. You don't need to be a programmer, but you do need to know the fundamentals of parallel computing to effectively use these machines. Remember that processes can be thought of as instances of programs. Threads run within a process and access shared data. MPI and OpenMP are libraries and standards that we use to parallelize code. Amdahl's law gives you an upper limit of scalability, but keep in mind that there are going to be other factors that impact scalability. And finally, know how to display your scaling data and choose your core counts. And then finally, and I believe that Cindy had posted this in the chat already, that we have a GitHub repo that shows the code that I used to generate the figures in this presentation. And you can use this code to generate your own scaling plots. So I don't have time to demonstrate it, but let me just one sec. Let me just share again. So if you go to the GitHub repo accompanying this talk, you'll see that there's a link down here for Launch Binder. Often takes a little while for this to start up because we're importing a bunch of the graphics libraries. Oh, that was actually pretty quick. And if you go here, let's go right to the Strong Scaling Study Notebook. Double click on that, and you can, I'm going to run all the cells. So I have all of the code in here for generating the scaling plots the wrong way, for generating scaling plots the right way. And then finally at the bottom here, if you wanted to generate your own scaling plot, you could take this and you could drop it right into your allocation request. I have a cell here where you could enter the number of cores, the times that you recorded. You could put some annotations in here and you're all ready to go. So with that, I'm going to stop, and I'm happy to take any other questions.